Welcome to the course on Industrial Automation and Control. Today we are going to have lecture lesson 2, which is on architecture of industrial automation systems. Industrial automation systems as a whole are quite complex entities. If you go to a factory, you will find a bewildering array of equipment, controllers, sensors, operator displays, various cabinets containing hardware. So all these together make a factory work like an orchestra. So today we are going to, since it's a complex operation with various kinds of equipment which harmonize themselves with one another, before we take a detailed look at each one of them, it is useful to look at the operation of the whole system and see how the various parts relate to each other. So that is the basic purpose of this lecture, to understand how this complex system is organized, what are the various elements in the system, how they relate to each other, what roles they perform, how they interact with each other. So that in short defines the architecture. So having said that, let us look at the specific instruction objectives of this course. So since the industrial automation system, being a complex system, is definitely organized hierarchically in various levels, so the first specific instructional objective is naturally to be aware of the various levels of industrial automation. The second objective is to describe the hierarchical structure of industrial automation systems, by which I mean that to know what these levels do, to be able to understand how one interacts with another, what information one accepts from another, and what information does it give to the other. So that will describe the hierarchical structure, then describe the essential functions that are achieved at each level, and specifically speaking, since industrial automation is, in a sense, a lot of industrial automation actually is concerned with control, and control is of two kinds, as we shall explain shortly. It could be automatic control or it could be supervisory control. So it is important to realize the distinction between the two. So the last instructional objective is to understand how automatic control is distinguished from supervisory control. So now let us look at the industrial automation pyramid as a whole. Why is it a pyramid? It is a pyramid because there are several levels. So it has a vertical dimension. So we have the lowest levels of sensors and actuators, which directly interact with the process or the machine. So they actually get the signals from the process of the machine. Now these sensors and actuators are actually act as the eyes and the arms of the controllers. So on top of these we have the automatic control layer, which is called level 1. Now a number of automatic controls are again managed at the supervisory control layer, which we call level 2. Finally, the operation of a particular shop floor as a whole is controlled. I mean, the whole overall manufacturing operation, including maintenance, production, quality assurance, inventory, everything is managed at another level which is called production control. And finally, right at the top we have enterprise control, which is more like a, I mean, basically consists of management functions, where not only the production related operations are considered, but even other operations like sales, marketing, new product development, everything is considered, and production is considered just as a part of it. That is level 4. Now at this point I should mention that while these functionalities are necessary for the overall control of a factory, but it often turns out that not necessarily all these layers are perfectly automated. What I mean to say is that generally sensors and actuators must be automated. There are equipment for it. Automatic control layers are also automated. There are most operations are not manually controlled. But from the supervisory control layer upward, it is not always true that you have computer based automation for functioning for performing the operations of that level. In fact, some of these operations may very well be done by human beings. For example, if you go to a power plant, or if you go to a big refinery, you will find that invariably on the shop floor you will have a control room. If you enter the control room, it is usually a very large room, where in the center of it you are very likely to find that there are a number of large computer monitors, and there are a group of people who are actually sitting around these monitors and constantly looking at these. So they are generally the process supervisors or the operators who perform a lot of supervisory control functions. So at the supervisory control level, there could be some functions which are automated, while some functions could be performed manually also. At the production control level, most of the operations, most of the time, are performed by humans with the aid of tools which help people perform the production control functions. So that's why we have what is known as a production manager, or say in a power station we have a shift charge engineer who is in charge of running the overall power system, overall power plant for a certain duration of time. So these production control functions are invariably a mix of manual as well as automated tools. Similarly, enterprise management functions are also like that. You have managers who use tools for performing their functions. So we have level 0, level 1, level 2, level 3 and level 4. Now having said that, let's look at these levels and their natures with a certain some more detail. So first of all, we'd like to point out, and this is why this system is called a pyramid, is because that as you go up the pyramid, the spatial scale and the temporal scale or the time scale of a given system at that level increases. Now what do I mean by that? So for example, consider one sensor system. One sensor system measures one process variable in the whole machine. So it looks at only that variable. So in that sense, its spatial scale is actually related, is actually very limited. So in the whole shop floor there are several machines. In each machine there are several process variables, and the sensor which is at level 0 only looks at one of them. So in that sense, it is spatially, its scope is very limited. Similarly, but its interaction is over a very small time scale, that is, it gives over sampling times, it gives values to the controller. So each value represents the variable over a very short time. So in that sense, it has a very each value which comes out from the sensor has a very short time scale. Now as you go up, for example, if you go to automatic control also works at the sampling level, in the sense that it computes control inputs for the plant at each sampling point. But while it is designed, sometimes considerations are made of larger duration. For example, when you say that the settling time should be low. Now when you are considering settling time, you are actually considering that if you make a step change, then from one operating point to another, how does the output reach from one level to another. So typically you are concerned about a duration of time which spans over several sampling times, right. So if you go to supervisory control level, one of the major functions is to change the set point, and set point changes are not made every moment. Control input changes are fed to the plant every sampling time, but set point changes are not made every sampling time. Definitely they are made over let us say typically some hours. If you take a power system boiler, so it will be say at 3 o'clock in the night it may be operating at 10% load, at 7 o'clock in the morning it may be operated at 25% load, at around 9:30 there is huge amount of load comes in the power system because all the offices open up and things like that. So between 9:30 and 11 o'clock it will ramp up significantly from, let us say, 30% load to nearly 90% load perhaps. Then that 90% load it will maintain till again, say, let us say 5 o'clock. After about 5 o'clock it will, evening will come and people will switch on various kinds of lighting loads. So then you will get the evening peak load. So only when the load will significantly increase will the boiler operating point be changed, right. So the operating point of a boiler typically gets changed let us say 7, 8, 10 times over a day, and its change is also based on the decisions for change are taken based on periods of hours, right. So in that sense it is on a larger temporal scale. It is also on a much larger spatial scale, because one sensor looks at one signal. One automatic controller may be taking control action taking several sensors into account. So in that sense its spatial scale is now increased. Now one supervisory controller will typically look after a number of automatic control loops, and it typically looks after one piece of equipment like a boiler or a furnace or a distillation column. Typically they will have many automatic control loops. Similarly, a shop floor may be made of several such units or machines. So the production control is done typically at the shop level, while the enterprise control is done at the overall enterprise level. So as you go up you can understand that the time scale is increasing and the spatial scale is also increasing. That is why it is a pyramid and not a cylinder. If you look at, so having clarified that, let us look at the nature of technology which is used for automation at these various levels. So at the lowest level, when you have sensors and actuators, so here you have mostly hardware. Things are either they are actual sensing elements, or they are packaging elements, or electronic circuits, or microprocessors. They are generally very hardware oriented. Nowadays we are also having software along with that, but the software is also very close to the hardware in the sense that they actually interact very close to the hardware and they are written specifically for that hardware. So in that sense we have a lot of what is known as embedded technology at this level. So this word embedded is because it is the kinds of, actually the sensor is supposed to be embedded in the machine. So all the this technology uses embedded hardware and software. When you go to the automatic control level, then it happens in many cases that it's a separate hardware. It's not embedded into the process, into the machine. It is a separate, tangibly separate piece of hardware which runs real time software. The software is generally generic, it is not very special purpose, but it runs on, often it runs on special purpose hardware like like PLCs, industrial PCs, or some DSP processors. So, but the algorithms are generally generic, like a PID control. PID control is a very generic control algorithm which is used for a number of process control applications. But the software is real time in the sense that outputs must be generated within a given amount of time, because every sampling time you have to generate the control inputs to the plant. So, you have real time software, hardware is special purpose or general purpose, both are possible. If you go to supervisory control, you will find that hardware is mostly general purpose, it's general purpose computers, of course with a strong data interface, because lots and lots of channels of data from the whole process come to this. The software is still online because the difference between what is a piece of software is called online if it interacts with the external world. So it works on the data which is continuously streaming in from the process using sensors and various communication channels, but it is not very hard real time. By hard real time an application, a software application is called hardware real time when the execution must be finished within a time deadline. If it does not finish, then serious consequences may occur and the system may fail. But these generally work, are generally a mix of mostly soft real time, in the sense that, well, things must be done in time, but they are not so hard, that is, if one does not one particular piece of computation cannot be finished in time, then some performance degradation may result, but in general the system as such will not fail. For example, one of the main purposes of this supervisory control layer is to update the man machine interface, that is, whoever is the operator, he has to be shown how the process is performing, plot the graphs, plot various statistics, etc. So these are typically soft real time operations, in the sense that obviously you cannot display a variable 30 minutes after you have got it, right. But as long as you display it in time, whether you are displaying it within 2 seconds or whether within 10 seconds is not of much consequence. So to that extent it is called soft real time. Software is, the hardware is general purpose, but the software is very special purpose. That is, supervisory control software for a refinery will be completely different from that of a power plant, which will be completely different from that of a let us say a manufacturing plant. So they are very specific to the machines, the software, but the hardware is general purpose. Production control does not bother about machines as such. They are not really concerned about, they take an abstract view of the factory. How many pieces of equipment are being produced per hour? Whether that piece of equipment is actually whether it's a gear or whether it's an engine box or whether it is nuts and bolts, it does not matter. So machines are looked at as general purpose service providers or material transformers. So you give a milling machine a blank, it will produce a gear. So what is the exact technology of the milling machine? It is not of interest at this offline level. What is of interest is how many pieces of parts it can produce, whether it is functional or whether it is non-functional, such things, right. So the software is generally offline, and it does use various kinds of algorithms, but they are of a totally different nature, and they are not concerned as such with the machines themselves, but take an abstract view of production. Similarly for enterprise level. So at these two levels, and to some extent at the supervisory level, we are not so much close to hardware, that is, we look at the process as an abstract entity and we take decisions about them and we analyze the performance, we also monitor them. So in that sense, the layers up to, from some parts of some parts of supervisory control as well as production control and enterprise control. I would like to term them as industrial information technology rather than industrial automation technology. You know, automation has a kind of hardware flavor. It has a kind of hardware, real time software kind of flavor. So while industrial information technology also contains lot of technology, resource optimization technology, scheduling technology, etc., but they are not concerned so much about hardware. They are generally generic technologies and they are non real time. So in that sense I would like to distinguish between industrial automation and industrial information technology. So in this course we will take predominant focus is on this, on the first three layers. We will see layer 1 and layer 0 very in some depth. We will also look at some automation technologies which are now being deployed for supervisory control. So that now another thing that needs to be said is that these layers actually exchange information. So sensors are continuously collecting samples of measurements which they are passing over to automatic controller. Similarly, the automatic controller is continuously computing control inputs which they are passing over to the actuator. Now similarly, the information that the sensors and actuators are that the automatic controllers are receiving from the sensors, part of it they are actually passing to the supervisory control layer to see whether the control loop is working satisfactorily or whether some set point change is needed. So or whether there is some malfunction, some sensor has failed and the process output is going out, in which case the supervisory controller must take some action. So it can either change the set point, or if there are two sensors it can switch from one sensor to the other. So it gives commands. So you can see that there is continuous information flow from the lower level to the upper and from the upper level to the lower. And as information goes up, because of the spatial and time scale, information continuously gets aggregated up. So you as you go higher and higher, you get more and more time averaged information over a part of the factory. As you come lower and lower, you get more and more detailed information about a smaller and smaller part of the machine. So as you go up, information gets aggregated. As you come down, information gets resolved. So there is resolution or refinement occurring. Okay. Now how do all these information flow up and down? Physically, how do they transmit? So nowadays, I mean, lot of stress is being put on. So there is usually a communication system which actually connects all these devices so that they can seamlessly exchange information, send results, in fact do a lot of configuration management, various kinds of things. So there is a if you see the industrial automation market, you will find a lot of activity here and some new trends emerging in the factories, which we will review in the course. So having got this kind of an idea about the overall industrial automation system, we would like to take a look at now we will like to take some more detailed look at these various levels. And before we do that, we must understand that much of this technology, much of the part of industrial automation that we are going to concern ourselves with is actually about control. So we should first see what are the elements of industrial control. So the structural elements. So what is basically done in control? Why do we control? We control because we want that the outputs or some process related variables, which could be temperature, which could be pressure, or we want them to behave in certain ways that we desire. So we have some desirable behavioral patterns and we want to achieve those behavioral patterns. That is, we want the temperature to, let us say, ramp up in a certain over time, then be held constant, then after some time ramp down, things like that. So obviously we achieve it. I mean, how do we achieve it? We achieve it by comparing the output with whatever we want, and then so to be able to compare we need to feed the output. So that is done by the sensor. I am sorry, this goes back, this has to go back, yeah. So right, so that you do by the sensor. Then when you compare, you get here, you get what is known as the error. So you give the error to the controller, then the controller node knows that what control input to give such that the error is minimized. Now the controller is actually basically a computing system, so its input is actually logical, it is not physical input. So before giving to the plant, in the plant if you want to change some process variable, you have to cause steam flow rate change, or you have to cause some motion change, some valve position change, etc., etc. So some physical change has to occur. So for that you need what is known as an actuator. So the job of the actuator is to produce a physical change which is proportional to the logical change which is commanded by the controller, and then hopefully if that physical change occurs, then the plant output will change in such a manner that the error will reduce. So this is the job of control. So now let us see. So we have identified the major elements. So the elements are sensor, actuator and controller. Now this desired value, where do we get this desired value from? This we get from level 2, that is the supervisory controller calculates this desired value. So here we have these two, we have level 0, here we have level 1, and here we have level 2. So this is the relationship. Now let us see each of these levels. So first let us look at a sensor. So sensor, what is the job? The job is to produce an information which accurately represents a physical variable, right. So obviously there is some variable conversion required. This information is generally first obtained in electrical form, and after that it is converted into pure information form using digital electronics. So what is necessary? Very simple. First of all, you need something which will convert the physical medium, let us say temperature, it will convert into some other form so that some electrical signal can be generated. So maybe the sensing element will convert this to a resistance change. Now this resistance change is still not an electrical signal which can be manipulated, so you need signal conditioning. So you put this resistance into some bridge and produce a voltage which is proportional to this resistance change. So all these are proportional, this is proportional to this, and this is proportional to this. So finally the voltage is proportional to the temperature. Now this voltage may contain various impurities, noise, etc. So you do further some signal processing on it so that you get more accurate voltages, or you increase its strength or do something. Then at this point you have got it in the information form. It is no longer a process variable, physical, neither electrical, it becomes information. So this information now has to be used. So used in what sense? So you can either display it, or you can transmit it to a controller, or you can store it in some database. So finally you have to use this. So here you may have a display. So by target handling element it could be a display, or it could be a network card. So it could be a network interface by which it will get transmitted, or it could be a disk on which it will be stored. So depending on the usage of the signal you have to deal with it. So basically this is, when you say an industrial sensor, you will obviously find a sensing element, you will also find some signal conditioning element. Nowadays because of ruggedness of electronics, the signal conditioning is getting transferred into the sensor itself. You can have some signal processing like filtering, and then finally it will be used in a display, right. So, this is a sensor. Now, let us take a look at some characteristics. So, obviously you have a sensing element. One thing that needs to be mentioned is that industrial sensors, apart from the basic sensing element, they also have other protective elements, like if you have a thermocouple. Basically a thermocouple is a, as we have seen that they are, as we will be seeing, they are actually two pieces of wires. Now, when you are trying to measure the temperature industrially, you do not put those two pieces of wire directly into the fire. So, what you do is you have what is called a thermo well. So, you put the thermocouple, those two wires, in the thermo well, and you put the thermo well in the furnace, so that it does not get destroyed. So, when I say a sensing element comes along with its all its packaging, and this packaging can have some effect on the control performance of the loops, because they have their own dynamics. Thermo wells have introduced time constants into thermocouples, as we will see. So we have a sensing element. Now, after the sensing element, we have signal conditioning and processing. So the job of signal conditioning is to transfer to electrical form, and then signal processing is to do further processing for some improvement, like making linearization. Suppose some signal is varying according to square, we want to make it linearly variable, so we can have a square root operation. We can have a filter to strip out noise. We can correct bias, we can add bias, whatever we want. So, in general, signal conditioning means that converting to an electrical form, generally analog, and then signal processing could be analog, could be digital also. So, you have analog electronic signal conditioning followed by digital processing. Now, digital processing could be of various types. Digital processing for what? So, digital processing could be for signal processing, let us say filtering. Digital processing could be for diagnostics, calibration, configuration. This is a very modern functionality. If you have a microprocessor, you have a lot of computing power at your hand. So, you can do more than just doing filtering. So, you can for example, you can perhaps detect whether the thermocouple wire has broken. So, whether the sensor is at all functioning. So, that is diagnostics. Okay. Does it go back? Okay, yeah. Oh, so it does not go back. Fine. So that is diagnostics. Sometimes you could have sensor characteristics sometimes degrade. For example, suppose a sensor develops a bias. You can have algorithms to actually detect the bias, and you can do its own calibration. You can send information that I have developed, that is, a sensor can send an information, or sensor can be interrogated, and you can find information that it has developed a bias. So, its readings will be interpreted accordingly for greater accuracy, or it can do its own configuration management. People send generic devices which are flexibly configurable. So, if it has a filter, what will be the time constants of the filter? That depends on what signal it is filtering, what is the bandwidth of the signal it is filtering. So, if it is filtering a flow sensor, its bandwidth will be larger than if it is filtering a temperature signal. So, it may be possible to even automatically set these filters. So, such things are done by digital processing. Plus, another major function is communication. So, nowadays sensors are all going to be communication enabled. So, they will either connect to networks, or they will connect to some remote terminal unit which will connect to network. So, there is digital processing done for this communication function also. Followed by, finally, there is signal protection and transmission. That is, after finally for everything you need to transmit the signal. So, you can have a network interface, or sometimes you can have a voltage to current converter. If you are having a 4 to 20 milliampere transmission, then you can have a voltage to current converter. if you are having RS422 kind of transmission, then they have specified voltage levels. So you have to have voltage conversion of that. So a typical, what I wanted to show is that if you come across a typical industrial sensor system, then what will it contain, and what it will contain, what all do they do. So if you buy a let us say a smart temperature sensor from a company, and or if you go through its brochure, then you will typically find that these functionality, some of these functionality will be supported. So having said that, let us look at the next element, which is actuators. So what do actuators do? Actuators, as I said, that they take the logical input from the controller and then they convert it to a physical plant input. That is what they do. Now obviously what is necessary for this? There is variable conversion necessary, and generally one thing is very much necessary is that these logical inputs are just logical, they do not have power, they have the information. So you have to do lot of power amplification. If you want to increase the temperature in a furnace, then just saying that you make giving a signal from a microprocessor is not going to do it. So you have to take the signal and then you have to move some big maybe fuel injection valve, and you have to change the speed of the fan which is putting air into the furnace, and you have to increase combustion rate, only then temperature will increase, right. So there are two things done. One is variable conversion, second thing is big amount of power amplification is to be done. So that is what is done by the actuator. Now actuators, now we have to remember that here we are having a very powerful thing, and not only that, we want to have precise control, because always our objective is to have precise control. So here is a very powerful thing which we will have to control precisely. So for that we always use feedback control. Therefore actuators themselves actually are feedback control devices. They themselves take feedback. For example, if you want to move a, let us say, I mean typical example, I mean non-industrial, but typical example is take an aircraft. When it is flying, then it has to move its control surface against huge amount of aerodynamic load, and these control surface motion must be very very precise. So unless you implement this actuator, which is the control surface actuator in this case, unless this or let us say the speed of a motor, unless you put these in a feedback, you can never achieve that precision. So therefore actuators are typically, the actuators themselves is a control loop. So they have their own sensors, they also have controllers, sometimes they have some analog signal processing. For example, sometimes it may happen that the controller may give some control input, but in that control input certain frequencies must be eliminated because they cause resonance, they may cause a lot of vibration, etc. So in such a case you can do some signal processing, that that input is given but that frequency is filtered out, maybe using a notch filter. So such signal processing may be done, and obviously power amplification, some amount of electrical power amplification is done. So you use what is known as servo amplifiers, will take weak signals and will accurately, exactly proportionally multiply them, but with lot of power amplification. Now after this, now you have some, actually in an actuator so much power amplification is necessary that it is always done in stages. So you have power amplification, first one level power amplification which is in the electrical level. So you take one electrical signal and increase its electrical power. But after that you have to, if you want to increase power further, often it happens that we go to different forms of energy. So we can have, if we have a motor driven actuator, then sometimes it is driven directly from the power amplifier, or sometimes it may be driven from using hydraulic or pneumatic devices. there are certain advantages, especially hydraulics can handle a lot of power in a small volume. So in a small hydraulic motor you can handle a lot of power. So when we have large power devices we use hydraulic and pneumatic. So they are also like amplifiers, they are also like power amplifiers, only they take an electric signal. So you have electro-hydraulic or you have electro-pneumatic typically actuators. Finally, at this point of time you have generated that necessary process input which you wanted to cause with a lot of power. So that will cause, now even that may go through. For example, if you have a hydraulic element, it will finally produce what? It will probably be applied to the stem of a valve. So that tremendous pressure will be created to the stem of the valve, which will, so still you have to have the valve because you want to control flow. So what you want to control here is flow, let us say. So for controlling that you need to move a valve. This is the final actual element. So you have a control valve. Now you need to open it or close it. Now how do you open it or close it? So you need to move its stem. So this hydraulic system will actually move the stem. This sensor will sense stem position, and this controller will give input such that the here is the desired stem position. So this controller will give input. So this is a total closed loop operated valve actuator which will control flow in the plant, which in turn may control temperature, whatever. So having understood this operation, let us now look at the actuator. What do you find? Just like we did for an industrial sensor, let us see what we are going to do for the actuators. So the industrial actuator systems, you will find again you will find electronic signal processing, you will find power amplification as we have said, you will find electro-hydraulic, pneumatic or mechanical elements, you will find feedback control for precision, exact value will be reached. You will find lots of auxiliaries because these devices have to be operated, they are generally power devices, so they need additional auxiliary systems for lubrication, cooling, filtering, etc. You may have subsystems which are used for remote operation. Some of these actuators need not be operated just from close, they may be operated from a distance, right. So regularly done in power systems where you have unmanned substations. So I mean, how do you close a switch or open a switch? You just from some remote control station you give a signal and the switch and the circuit breaker opens or closes. So the circuit breaker is the actuator. Similarly, for safety you may find lots of various kinds of pressure release valves or various kinds of interlocks, because these are powerful devices. So if they malfunction they may cause accidents. So special systems are used. Similarly, since they consume some amount of energy, you will find special systems which will try to save energy in the actuator itself. So some freewheeling or some switching off unnecessary energy devices, you may find technologies for this. So typically this is what you will find in an industrial actuator, and we then in the future classes we will look at various kinds of industrial actuators in detail. So now we have covered sensors and actuators in level 0. Now we come to level 1, which is an automatic control loop. We have already seen the automatic control loop. We at that time we have seen the structural elements of the loop. Now what are we saying? Now we will concentrate on what the loop is going to do. What is the job of the loop? As I said before, the job of the loop, this has changed. Let me go back. Yep. Let me lock this. So, the job of the controller is to maintain the set point, that is its job, which is given, comes from the supervisory control. So why should the set point change? Why is it once I set it carefully, why should it change? It changes because of disturbances. For example, suppose you are cutting metal. Now the metal is inhomogeneous, that is the metal which you are cutting, that is a piece of, let us say, steel, is not homogeneous. You have set a particular cutting speed, depth of cut, feed, you have set, and the machine is rotating. Now suppose there is some parts come where the material density is different, then the speed will fall, speed may fall. So if speed falls in metal cutting, the quality of cutting suffers, and you have no control over what kind of material qualities will be supplied to you in the raw material. So, or for example, suppose you have a rolling mill. So in a rolling mill, the load on the shaft depends on two things, depends on the material that you are rolling and depends on its temperature. In fact, that's, I mean, we are talking about hot rolling. So as you are varying, so if the temperature varies, the load on the motor will vary enormously, and therefore the speed will vary. Now you don't want to allow that. So what I am trying to say is that because of these load disturbances, if you set a particular speed, that may not be obtained. So to ensure that, you have feedback control, right? Plus there may be sensor noise also. The feedback may be erroneous. So it is basically because of these two that the control problem becomes non-trivial. Plus many other things may happen. For example, one of the things that is very regularly happens is that the actuator saturation. This is a very regular thing in actuator saturation. That is, the actuator cannot really drive enough input into the plant as the controller wants. Actually, the controller makes unreasonable demands on the actuator cannot give. So it is because of these things that the control problem is not elementary, and you have various kinds of difficulties. So we will look at now, having said this, let us look at the various kinds of things that you find in an industrial controller. Oh, sorry. So let's look at automatic control. Automatic control, again, I must mention this I have not mentioned, can be of two types. The first type is what I call continuous variable control. That's what we are familiar with. We have already, most of us have taken a course in that called automatic control systems or control systems or control engineering. So there we study mainly continuous variable control, where we are interested in controlling the value of a variable. Let the temperature be 200 degrees centigrade. That kind of control, where the temperature is a continuous variable in the sense that it can continuously vary over time. It can take any value. So this control, we control analog continuous process variables. That's fine, and typically we apply what we understand by closed loop control, which you have seen. So the main objective is to track or hold set points, that is, the output should follow the set point. If the set point changes, it should track it. If the set point is constant, it should hold it irrespective of disturbances. So it should reject disturbances, both in the sensor as well as load disturbances as well as in the actuator. Now for this purpose, it is said that more than about 80-85% of all industrial controllers are a particular class of controllers called PID controllers. So they are generally, these control algorithms used are generic, though in some cases you may use some special purpose controllers. Now because they are generic, they have to be tuned for a specific plant. So, you have to set controller gains for that specific plans, and that is called tuning. So, these controllers are tunable and they require tuning from time to time, and they are implemented typically on digital real time systems, like basically a processor system with an interface with the sensors and with an interface to the actuators. So, it's a kind of microprocessor based system, and these are generally very inexpensive. Typically a control system is less than 5% cost of the plant it controls. So, the controller is actually very cheap, although it does a very critical job. So, now this is what you find in automatic control. Now, let us automatic continuous variable control. Similarly, you have sequence or discrete event control. Now, in discrete event control, what you have is that you have control of discrete valued process variables, that is variables which cannot take continuous values, but either they take discrete values like on and off or low, medium, high. So, you have to control. So, now you see values are all constant values. So, there is not much point in trying to control the value. So, what do you control? So, you try to control the sequence. So, what happens after what, or you control timing, that is when exactly will this valve close, that is 5 minutes after the valve opens you should switch on the pump, and similarly 2 minutes after the pump is switched off you should switch off the valve. So, such control is called discrete event control. So, obviously they use sensors which are also discrete, that is they like limit switches just sense whether something is in this position or that position. Pressure switch senses whether the pressure is high or low. Photo switch senses whether a part is placed on the conveyor belt or not. So, you use this kind of sensors. You have lot of interlock or alarms. So, you do interlock and alarm processing in this. Typical hardware which is used for discrete event controllers are programmable logic controllers, sometimes industrial PCs, and sometimes could be very special purpose dedicated processors, right. So, they obviously do not need tuning, and they are so you have status sequencing and timing control. So one good thing about them is that unless the control logic changes they do not need tuning. So, this is the story of automatic control. Now, we will one last thing that we will consider here is supervisory control, and we will stop here today, because production control and enterprise control are functions which we are not going to cover in great detail in this course. So, we will introduce them later if we have when we have one or two introductory courses, introductory lectures or lessons in this course. So, let us look at these pictures. This picture explains what a supervisory controller does. So, previously we had seen one control loop. Now, I am fine. This is the process that we want to control. So, this is the process. This is the feedback of the control loop. But we are having a number of controllers here. So, suppose one controller is working. So, as we have said that what does a supervisory controller do? It gives command, it gives set point. That is, the automatic controller just maintains a temperature. It does not know what temperature to maintain. If it is told that you maintain 200 degree centigrade, it will do its best to maintain 200 degree. But whether to maintain 200 degree or to maintain 115 degree, that the automatic controller does not know. That information must come from the supervisory controller. So it gives set point, but it does another very important thing, that is, it is not always that you are going to use the same controller. For example, the controller that you may be using during the time that a plant is started up from, let us say, cold condition, or when a plant is shut down they are actually totally different control laws. So, you may have more than one control law. So, if you are doing startup, you use this controller. If you are doing shutdown, you use another controller. When you are doing normal operation, you use another controller. So, you must give commands as to which controller to use when. So, that command comes from the supervisory controller. So, it gives various kinds of commands. For example, suppose there is some accident, or there is some malfunction in the equipment. Immediately you have to do emergency shutdown. So the supervisory controller must understand that there is a malfunction. How does it understand? Because it also gets the process inputs and outputs. So based on these process inputs and output, it does lot of calculation to always check whether the system is working nicely. If it finds some problem, immediately it will give various commands to ensure which controller to use when. So, a supervisory controller actually manages a number of automatic controllers, right. So, having said that, let us see its basic oh, I see so what are the features of supervisory control? I am sorry, what is this happening here? Oh, so first point is set point computation. One very important thing is that set point computation is very important in manufacturing from the point of view of energy, quality and production volume. Unless you give proper set points, you will not get product of certain quality, you may be wasting lot of energy in producing it, and the amount of production will also fall. So that is why supervisory control is so critical, and it is often done by very experienced operators manually. So it is very critical for manufacturing. So it does startup, shutdown and various kinds of emergency operations. It does control reconfiguration and tuning. You may have to change the controller from time to time. It does performance monitoring. Is the loop properly tuned? Is there a sensor malfunction? It continuously checks. It provides an operator interface. It provides with nice graphs to the operator who also sees. They are generally based on, obviously all this can be done based specific to an equipment, it cannot be done otherwise. So, and they work, as I said, in hard and soft real time scenario. So having said that, they are also very expensive because they are specific to a process. We will skip this slide altogether because we do not want to. So we are just looking at the various elements in this thing, like product process scheduling, material handling, maintenance management, inventory management, quality management and resource optimization technology. They are, as I have mentioned, that they may be online, but they are non real time. Some of them may be online. So finally we have a lesson review. So what we have done in this lecture, we have looked at the hierarchical structure of industrial automation. We have looked at level 0, the sensors and actuators, what they do and what technologies are found in them. We have looked at level 1, automatic control. We have also looked at continuous variable and discrete event control and distinguished them. We have looked at supervisory control and we have understood how they are different from automatic control. And finally we just took a cursory look at production control. Enterprise control we are not going to even have a look at, not going to have a cursory look at, because this is essentially a business management operation. So here we have some problems, points to ponder. For example, can you explain the differences between continuous variable and discrete event control? Can you cite 2 or 3 differences? Can you draw the block diagrammatic structure of an industrial sensor and give an example? Let us say you locate some industrial sensor and then try to identify that what are the various block diagrams, I mean what are the various subsystems in it, what are their functions. Can you define automatic control and distinguish it from supervisory control with an example? And finally, can you state 3 major functions for each level of the automation pyramid? So these are problems for you to ponder on, and thank you very much.